talk briefly about the Snell's Law lab that we did yesterday. With Snell's Law, it deals with what happens to light as it's going from one medium, one substance, to another. Oh, here we go. I didn't unplug and plug this in. So I'm going to put an interface, a boundary between two. Maybe. Good. We're going to have a medium 1 and a medium 2, and all that means is that 1 is typically what we label the place where the light rays start, or at least are at the beginning of our consideration, and 2 is where they are otherwise, or after what they pass into. So on this, I'll do a blue line for our light. The light comes in here, and what you saw, you actually had another interface underneath that going back into air. So let's set this up similar to what you had. And let's say that medium 1 is air, medium 2 is the lucite plastic that you use. Okay, and then to sketch this out, I ask you to draw a normal line. Nailed it. What happened to that ray you were tracing through the lucite block as it went from air into the lucite?
It's like 1.5.
What do you mean it's 1.5 times?
Like when you plug in the sine over sine.
Before that, just what happened to this ray that we were tracing through?
It gets reflected or distorted.
It gets bent,
Yeah.
would be a better term. So how did it get bent? In what direction? Did it like curve off, or
It went closer to the normal.
closer to the normal line? So the light that we're looking at here is not going to curve through these things. It only changes as it goes from one medium to the other, and then it continues to go straight in everything that we're going to look at. And as David noted, the angle that it hit the normal with was reduced as it got into the plastic. So we label that theta 1 and theta 2 measurements from the ray to the normal. And then you saw it bend back to the original line, or the original angle, as it went through the other side. So that's a little different. And then the last part of this was, now compare these. What do you see when you compare these two angles, and how are they related? And they're related by something called an index of refraction. So that if you took the, if you took sine of the first angle divided by sine of the second angle, the one inside, you got a constant that we'd label N2, called the index of refraction. Refraction means bending here. And it's a description of how much light bends, essentially, going from one medium to another. But it's also a measure of the speed of light in that medium. The other way to look at this is that N is related to the angles that we'll see, but in a more basic sense, it's related to the speed of light, c, which is abbreviated c, divided by the speed of light in that substance, which we've labeled v. And c here, for those of you who were in last year, remember, is 3 times 10 to the 8 meters per second. And that's the speed of light in a vacuum. So we always compare it to the maximum speed of light in a vacuum, but light actually goes more slowly in in everything else. Even air. Air is actually very close, but a slight bit slower than speed of light in a vacuum. So this tells us, or this measurement tells us what it is, although it's not 100% true, because this assumes that we're only looking at this angle, and actually we also have to consider the effect of whatever our first medium is on the speed of light when we want to be most accurate. And so while this is really, really close and will give us a very good agreement to what the index of refraction of lucite is, that's only because it's coming from air. If the light was first going through water and then the lucite, we'd see quite a different relationship. And that's because when you back out and you do all of Snell's law, it's actually a comparison of the two substances. Medium one, in our case the air, will also have its own index of refraction. And then you multiply it by the sine of the angle that it makes with the normal. That is a constant. So this is then equal to what you found, n2 sine theta 2. The only difference that we had in the lab is that we put this as 1. Air is extremely close to 1, and for our purposes, it is equal to 1. But we kind of ignored that when we were looking at the lab. So when we're actually performing calculations from here on out, we'll use this as Snell's law. He was it's in your readings, either a Dutch or a Flemish physicist who did this first. And we can use this to describe any kind of interaction. If we had another interface down here, where it maybe went into water, say, so from air to the plastic to the water, all we do is, I call this medium 3, I'd say I want to look at now this change. What happens as it's going through there? So let's see if we can predict something from that based on what we saw in yesterday's, and then we could even do a quick calculation to show it. What did you measure for the index of refraction of lucite? What did you get for that n value at the end? Alex?
It was the average of the index of refraction was like 1.47.
Does anyone have, can anyone confirm that?
We got about 1.55.
1.5, so right around in there. Let's make it easy and just call it 1.5. We could look up a really well agreed upon value, but for our purposes 1.5 is pretty close. Oh, I would expect something right around there. Water has, and I'll call this N3, has an index of refraction of 1.33. Okay, so the speed of light in water is about 2/3 what it would be in air. 3/4? 3/4. So let's see if our ray hits here. Let's see if we can predict what's going to happen first, and then we'll actually calculate it out. So let's say that we're going through, we're following this ray, and this ray strikes the interface between the lucite and the water at an angle of 15 degrees. That'd be our theta 1 is what I call it. We could label it theta 2 and theta 3, that's fine. What's going to happen to that as it goes through into the water? Is it going to bend more towards the normal or away? And so this is just a way to look at, what do I expect? So let's replace these with 2, 2, 3, 3. Well, N2 is 1.5, so that's greater than N3. What does that mean for the relationship between sine of theta 2 and sine of theta 3? Which one should be greater? Sine of theta 3. To make this possible, sine of theta 3 should be greater than theta 2. So what should happen to our array? Which way is it going to get bent?
Away from the normal.
Away from the normal. So that sine of theta 3 is bigger. So that's what we expect. We'll go through and calculate it quick to see if that's what we get. So somewhere out like that. let's see what we get. So if I want to find this angle, I'm going to rearrange this. I'll divide both sides by n3. Times the sine of my first angle that hits. And then I'll have to take the inverse sine of that. So theta 3 is equal to the inverse sine. N2 we said was 1.5. N3 for water is 1.33 times the sine of the angle that it hit with, which was 15 degrees. Somebody help me out. Troy, I know you know how to use your calculator. It's funny because he just got in trouble for using it on a math class, in a math class.
I got 0.8.
Are you in radians?
Yes. Dang it, no, I expected.
What'd you get, Troy?
I got 16.97.
So 17 degrees. We'll wait for someone to confirm. 17 degrees. So not a lot, but it did definitely move out. If it had been into air, which has an even lower index, it would have been that much farther.
What was the original theta?
What are the units of theta?
Oh, I was wondering what the original.
Oh, I always use degrees.
It was 15.
Yeah. What are the units of index of refraction?
Like Newton's or it's Snell's.
Snails.
It's just a number. Yep, absolutely. We call it unitless because we've got the same units on the top and the bottom of these two. And so they cancel out. Sines, they don't have units. They're just numbers. So all of this is just a number. So no units on index of refraction. As Cody pointed out, it is very much like the coefficient of friction. It's just a number that describes this thing and modifies something else. Today's work then is going to be work time on some Snell's Law homework. Tomorrow I'll be gone with Knowledge Bowl. I'll have the materials out. It's a lens lab, very much like our first mirror lab where you were just experimenting and looking at the qualities of lenses of the two different types. And then Friday we'll have another dark room lab with images and things.